Hi, this is Dr. Lesher, and this is a video about enthalpy of formation. So we've talked about enthalpy in class. It's the heat change associated with the reaction. And we're going to talk about formation reactions, which are a certain class of reactions with a couple criteria. Meeting these criteria make them formation reactions. So one of the criteria is that a formation reaction produces a mole, 1 mole, coefficient of 1, of the chemical substance. And it creates that substance from the elemental forms of the elements that make up the compound. And those elements are in their most stable and common forms. These reactions, they're not terribly common. Like, they're not reactions that happen really often, but we think of them as reference reactions. So, for example, iron oxide, iron 2 oxide, to write a formation reaction for it, we would start with iron. Metals in these formation reactions are just written as elements with nothing else. And then oxygen, but since oxygen is a diatomic molecule, we have a coefficient of 1/2 to show that there's just one atom of oxygen in that final product. And we have tabulated values for the enthalpy changes associated with these formation reactions. Oops. They've all been measured. So for this particular example, the enthalpy of formation of iron 2 oxide is negative 272 kilojoules per mole. So a few more details. This is like a template for formation reactions. Formation reactions kind of have to follow these rules. So one is that there's just one single product, and it has a stoichiometric coefficient of just 1. And then, like I said before, all the starting materials are elements in their most common, stable chemical form. So both the phase, whether it's a liquid or a gas or solid, and whether it's a diatomic molecule or not. And the enthalpies of reaction, when there's gases involved, they do vary with pressure. If there's solutions involved, they vary with concentration. So concentrations and pressures must be specified, and really they must be in the standard state. So if you've got gaseous participants, their pressures are at 1 bar. For solutions, the concentration is 1 molar. So this is the standard state. This also includes a temperature of 25 degrees C. So you'll see this symbol for the enthalpy of formation. Delta is our change, so the enthalpy associated with the reaction. H for enthalpy, the subscript F indicating it's a formation reaction, and then the little degree symbol, that indicates standard state conditions. So let's look at a few examples. We already looked at iron oxide. Bromine. So bromine's typically a liquid at room temperature, and so to get it into the gaseous form, we can write a formation reaction for that, and it's just showing the conversion, the change of state from liquid to gas. And to do that, the enthalpy of formation here is a positive 30.9 kilojoules. That makes sense. We're inputting energy into the system in order to convert from liquid to gas. And nitrogen monoxide is half a nitrogen and half an oxygen to form nitrogen monoxide. There was a mistake on your slide there. There should be a little 1/2 before the oxygen. A more complicated compound involving a few elements, methanol. Carbon's most common form is solid carbon in the form of graphite. There's a total of 4 hydrogens in there, so we would need 2 H pluses. And then there's just the 1 oxygen, so we would need a half of an oxygen again. And so those all have enthalpy changes associated with those reactions. If we were to look up the enthalpy of formation of an element in its standard state, like if we saw that in a reaction, for example, carbon in the form of graphite, there's no reaction to go from carbon graphite to carbon graphite, so there's no enthalpy change there. So why do we look at these reactions? What does it do for us? We can look up all of these delta H of formation values, all of these enthalpy of formation values for almost anything. And we use that as a reference point so that we can calculate the change in enthalpy for a more complex reaction involving lots of compounds and different things. So we can do this because enthalpy is a state function. This slide is not in your notes, but this appendix is from the textbook. If you scroll all the way down to the bottom of the listings of chapters, 1 through 20 or whatever there is, you'll see a link for Appendix B. And this is where you can find some of these values. So you'll notice that there's all sorts of compounds listed in here involving all sorts of different elements, and you can look up the enthalpy of formation for any of these compounds. So let's look at how this applies and how we use the standard enthalpies of formation to calculate the enthalpy change for a reaction that's not a formation reaction. So the reaction we're going to look at is two nitrogen dioxides combining to form dinitrogen tetraoxide. And we can look at this reaction as two steps. So the first step being that the reactants, the two nitrogen dioxide molecules, decompose into the elements in their stable common forms. So for the case of two nitrogen dioxides, that would break down into one diatomic nitrogen molecule, N2, and two diatomic oxygens, 2O2. There's a little mistake on this slide as well. This next step here, this green arrow pointing up, this arrow is showing those elemental forms, the nitrogens and the oxygens, forming N2O4. So you can see we've got just the right number of atoms. We got 4 oxygens altogether and 2 nitrogens. And so the formation of dinitrogen tetraoxide, that formation happens when those nitrogens and oxygens come together. So what we're doing is looking at this reaction as a series of 2 steps, and the overall enthalpy change for the reaction of 2NO2 to N2O4 is the sum of this decomposition step, the big downward arrow, and the formation step, the smaller upward green arrow. So if we know the 2 values of those enthalpy changes, the enthalpy change of the reaction is the sum of the 2. So let's see how that plays out and how we can use these looked up values to actually calculate that enthalpy change. Another way to look at this is looking at these reactions. So the decomposition here correlates to that first downward arrow, and we're seeing 2NO2 decomposing. Second reaction here is that formation reaction, so the formation of N2O4. What I do here is basically add these 2 reactions together, and one way to think of it is this. If you have a decomposition here that results in a nitrogen molecule and 2 oxygen molecules, and then that nitrogen and 2 oxygens get used in the second reaction here, overall there's no production or loss of the 1 nitrogen molecule, the 2 oxygen molecules. They were produced in the first step, used in the second step. And so when we sum together 2 reactions like this, if the same molecules are present on the right side of one reaction and the left side of another reaction, they kind of cancel out. And so summing together these reactions, the formation and the decomposition, give us this overall reaction that we're trying to figure out the enthalpy change for. We're trying to figure out the delta H of reaction for. So we know that if this is a formation reaction, we can just look up what the value of this enthalpy change is. This decomposition, though, this is not exactly a formation reaction, but it's related. So let's see how they're related. This slide is also not in your notes, but I would like you to take a couple notes on this anywhere in the blank space on your lecture handouts. So this is the summation of these 2 reactions that we saw in the last slide. So we can look up the enthalpy change associated with this one because it's, by definition, it's exactly what I said are the criteria for a formation reaction. The elements in their most common forms summing to make 1 mole of the product. So we can look up that enthalpy change in Appendix B in the textbook, and it's 11.1 kilojoules per mole. Now the decomposition, NO2 breaking into those elements, that's not a formation reaction, but I can look up the enthalpy of formation of NO2, and I can get a number for it. So how does that number relate to this reaction? The formation reaction for NO2 would be half of a nitrogen plus an oxygen to give us NO2. Going back to my definition of what a formation reaction looks like, I have 1 mole of the NO2 and I'm kind of using the stoichiometric coefficients that give me the right number of atoms. So that enthalpy change is 33.2 kilojoules per mole. Now, up here, the NO2 is on the left side. It's a reactant because we're decomposing it. We can flip the formation reaction with a half nitrogen plus 1 oxygen. We can flip that in reverse, and we will know the enthalpy change associated with that reversed reaction because, like with overall energy changes, the enthalpy change, since it's a state function, of the reverse reaction is equal in magnitude but opposite in the positive or negative. So the enthalpy change associated with this reverse reaction is negative 33.2 kilojoules per mole. And then finally, we need to match the stoichiometry of this now decomposition reaction to what's actually in our goal reaction. And so we need to scale it up by 2. So what we're going to do is multiply through this whole reaction by 2, and that means multiplying all the coefficients by 2, so 1 becomes 2, a half becomes 1, 1 becomes 2, and then also scaling up the enthalpy change associated with that reaction, because if we have twice as much, we're in this case giving off twice as much heat. So the enthalpy change associated with that scaled up reaction in the form of the decomposition is negative 66.4 kilojoules per mole. So now that I know the enthalpy changes associated with the decomposition at this stoichiometry and the formation, the sum of those is my enthalpy change for this reaction that I can't really just look up a value for. So that's how we can use these enthalpies of formation to predict, to model the enthalpy changes associated with any reaction.